Alright, so I have this random vector here in the complex plane. So it's a 2D vector, and say we wanted to rotate it like 90 degrees or pi over 2 radians counterclockwise. So to do that, you would multiply by I, and you would get 7i plus 5i squared, which is 7i minus squared minus 5 plus 7i. And yeah, so you'd be somewhere around here. And of course, if you like multiplied by another I, so if you multiplied by I squared, you would be 180 degrees off from where you were. You'd be somewhere there. Another way you could do this is using Euler's formula. So e to the I theta is equal to cosine. I'll just type it. I yeah. I'll actually just do this. Inventory. Okay, so yeah. So if we have some random, like let's just say x plus 1, right? And then multiply it by cosine x plus I sine x. Yeah. So you would get x cosine x uh, plus xi sine x, and then plus yi plus sine x, and then plus y I squared sine x, so minus 1. And you could combine the real and imaginary parts. So, so this is a real part, and yeah. So yeah, you'd get x cosine x minus y sine x plus I times all of this. And so if you actually take a look at this, so yeah, so actually this is a 2D rotation matrix, which is cosine x negative sine x and sine x. And then cosine x. They're not really all the same size. Nah, that's about similar. Yeah, so that's a 2D rotation matrix, and it you basically get you can get that by like so I don't know. Let's yeah, we'll just we'll just use this same thing. Let's just, yeah, we'll just use this one. Okay, whatever. It doesn't really matter that much. But, so, let's just say we have this random vector here that's r, has magnitude of r, or length of r. And then we have theta here. And then, if we have another vector here that's like also r, I'll just delete this r. So say they both have a radius, or say they both have like say they both have a length. So they both have a length, or magnitude of r, and then this one's going to be alpha. So yeah, but anyways, so we could say this original vector would be, we could write as r cosine theta should we say that or something? Because it's like gonna be very long. So that's gonna be r cosine. But anyways, all right, let's just use it. Next would be cosine theta for the x and y coordinates. So that would be this original vector here, which would be, let's just say, x1, y1. And then the other vector would be, okay, I'll just do this. But the other vector, which would be x2, let's just say it's x2, y2, would be r cosine alpha plus theta. Okay, you know what, guys? I'm actually just gonna. All right. Okay. Let's use it. This is really hard to do. Why isn't it? Blur? No blur. So let's say this one. Okay, let's just call this angle x, and let's call this. Let's just call this angle A, angle B. Simpler. Okay, that's a B. Okay. A plus B. R cosine A plus B, and then the y would be R. I mean A. Yeah. So that would be those two, and then so R cosine A plus B and R sine of A plus B. So what you can actually do now is this is going to be equal to R times the cosine of A plus B, which would, using like the trig identities, the basic trig identities, you get R times cosine A plus B, which would equals and minus A. And yeah, so that would be the X. Well, and then, so that would be the X one, and then the Y one would be R times sine A plus B, which would be sine A plus B plus. Okay, so then you would, so then what we said that our cosine is X and our sine A is Y. And what we can do now is actually say, okay, our cosine A is X, so X cosine. And then our sine A is Y. So minus X on the, and then our sine A is Y, so Y cosine. And then our sine, our cosine is X, so Y. I think, our cosine, yeah, and then you could swap these two because you're gonna add them, so it doesn't really matter. Wait, this seems off. No, our cosine A is X. Oh, X sine B. Yeah. No, wait, what? X sine B, yeah. So X sine B. Okay, let's just double check. R cosine A is X, so X cosine B. R sine A is Y, so Y sine B. R sine A is Y, so Y cosine B, and then R cosine A is X, so X sine B. Yeah, so I think that's it. So then basically you would get this matrix because you can you can if you actually and then you would get this matrix and you can multiply it by like you would well we factored out x1 y1 or we took out x1 y1 and then because so if we do x1 times x cosine x. Oh wait, no. So, well, we can remove the x and y's to get. Yeah. Okay. Wait. What am I doing? We can remove these. Yeah. So now, okay. Yeah. We can remove those to get basically just these trig functions, and then when we actually multiply by the original xy, we get x cosine b minus y sine b, and then because you do so x cosine b minus y sine b, and then after I'll just write it on the right then. You get x sine b minus y sine b, I think. And then you get x sine b plus y cosine b. X and b. Alright, hopefully this is correct. Whatever. Okay, x sine b plus y cosine b. And then if you actually take a look here, x cosine a minus y sine b, x cosine b, and then x sine b plus y cosine b. So yeah, they match. And that's the rotation matrix. The 2D rotation matrix. And yeah, that's basically it. That's another way you could do it. Okay, I forgot, but another way you could do it is using the polar form. So you would do, because the polar form is basically like r cosine x r times cosine x plus r times I sine x, and which eventually would be r, you would factor out r to be r times this, which would be r times e to the ix. And then if you multiply by e to the ix, you would get, oh wait, oops. So because this is a new angle that you want, we can just say e to the I theta. You would get r times e to the ix plus I theta. You would factor out the I. You could think of it so because the r, or the magnitude, or the length of the vector is still the same, but then all you're doing from the original one is just adding this new theta. So you're just going around more. So if I delete this, you're just going around this way more. And yeah, I mean, that's it. That was actually probably a much easier way. Okay, so that's sort of how you do 2D rotations. But then what about 3D rotations? So from what I hear is that people prefer these things called quaternions over your standard Euler angles because they prevent gimbal lock. So for example, like say we have my MP6050 drone. The MP6050 has a gyroscope and accelerometer. So like let's say for example that we pitch the drone 90 degrees down. So we're going very fast. Then like, so if we do that, then our x and z axis will get aligned, and then we lose that degree of freedom. And then like, so we can't really tell the difference between if we because if we we're rotating around the z-axis and z and x-axis in this case, and then if we roll, we're also doing that, so we can't really like know which one is which, or like we can't really tell the difference. And anyways, well, the gyro can't really give you really accurate pose estimation anymore, or like sorta, I guess. But then so that's an issue. And then the accelerometer might help out a bit because it knows like where direct gravity is, or like relative to the drone. So yeah, but so anyways, people prefer quaternions over like your Euler angles because they prevent gimbal lock. From my understanding, I think it's because quaternions have a quote-unquote fourth gimbal, and quaternions are like numbers represented in 40, but my peanut-sized brain cannot comprehend quaternion 40, or so and I can't really understand quaternions. But this is a very useful post, and so essentially quaternions can be represented like w plus xi plus y j plus zk, where this is and then that's sort of the amount to rotate around it. So that's essentially how they are represented, kind of. But yeah, that makes it like more easier to understand for me. Where like I corresponds to the x-axis, so I like corresponds to the rotation around the x-axis, and j to the y, and k to the z. And then so like well, the guy who like kind of I think William Hamilton was the guy who like created these. Like he said I squared equals j squared equals k squared equals ijk. I don't really understand this because I don't know. I squared equals j squared equals k squared equals what? Because like if you rotate it, I don't know, my brain is dead from looking at this. But yeah, so